Okay, welcome back everybody. We're going to continue with this Bayesian example I just sent you guys before we kicked on the class and started filming Bayes' likelihood times prior. And that's it. So Bayesians always do that. So what is a Bayesian? Somebody that operates off of a posterior. So they build a posterior distribution. So what's a posterior? So the posterior distribution is just likelihood times prior. So I'll write down proportional to the likelihood function. We have to get a sense of these, so I think an example will help us, times the prior distribution. So likelihood and this is the prior. Sometimes people call this the model, but I call the whole thing the model. So the whole thing is part of your model. There's a lot of language that probably people are arguing over, but this is what a Bayesian does, is they take the likelihood function and they multiply it by something. If you want this to be equality, so I can get rid of that proportionality sign, I can normalize everything. So this is, in your probability class, your typical normalizing constant. You integrate over the function. And in our case, this is going to be 0 to 1. So a lot of times I'll write omega p to say I'm integrating over the whole space. In our case, for our example that we're studying, p lives between 0 and 1. We'll recap that in a second. But a Bayesian is always doing this. They're constructing some function, and that function, the whole shape is here. So the shape of the function, how it wiggles around the space, is defined by the likelihood times the prior. This is the posterior distribution, and I guess in terms of the nomenclature, what people mean is this is the thing that you believe after you see the data. So this is after data. Where the data is that, and it's fixed in the equation. And the prior is before the data. So I don't love this, although sometimes I think about it this way, that this is what I believe about P before I see the data. Now that's probably not a good way to phrase things in general because I might not have actual beliefs, but I'm doing something mathematically. I'm trying to give my posterior, what I do inferences on, some properties. And we'll have to talk about that a little bit. This is not a full-blown Bayes class. I think I'll take you through conjugate analyses, and there's another class on campus where they'll take you through a lot more different viewpoints of Bayes. But one thing you can say about a Bayesian is they're always, at least in spirit, talking about likelihood times priors. You can think about this as penalized likelihood, that there's some sort of a penalty or some sort of a regularizer, some sort of dampening of the space. A lot of people do that. And if we talked about it like that, maybe we'd all agree. Saying that, this is a distribution, a probability distribution on P. And so Bayesians will take advantage of that, and they'll integrate over that function. Where I've seen a lot of people play around with regularized likelihoods, and they'll maximize them, and they won't integrate it over them. And they'll say that it's something different from Bayes. Saying that, a Bayesian might do that exact same thing. So a lot of times, people do the same thing, but they call it something different. And we're going to be talking about that all through the remainder of the class. Let's just put some context to this. So let's think about an example where xi's are Bernoulli. So that means, at least in the way I'm writing everything down, xi's are either 0 or 1, and the ones happen with probability p, and the zeros happen with probability 1 minus p. And we're going to collect n data points. So another way to write this down, right here, of course, I'd probably have to give you a full description of what P is and what N was. I'd have to tell you that there's N of these, but I could write down the model like this. So I could say this same exact thing can be described this way, that xi's are either a 1 or a 0. They happen with probability p, or 1 minus p. That's nice. I can write it down. I can think about it. I can think about coin flipping when I write this down. And then I could write this down like this. If you want my eyes on there, that's fine. I'll put eyes on there. So I could write this down more compactly, like this. And so the xi's are acting as indicators. So when the xi is 1, that's p to the 1, 1 minus p to the 1 minus 1. So that's p. And when the xi is 0, it's p to the 0, so that's a 1. 1 minus p to the 1 minus 0 is 1 minus p. So it says the exact same thing as this says. But I like this form because I can code that up in terms of an equation. They all mean the same things. And if I wanted to write down the full sampling distribution for everything, I could write it down like this. So my sample, in this case, is x1 to xn. And I could write that down like this, which is just the product from 1 to n, p to the xi's, 1 minus p to the 1 minus xi's. And I could write down the likelihood function. And on the board, the likelihood function looks exactly the same as the sampling distribution, but they're entirely different creatures. So one is a function of p. So this is a function of p, where the x's right here are fixed. And in terms of the sampling distribution, if I want to talk about the probability of the x's, p is fixed. I can't talk about the probability of the x's until I say what p is. And so while algebraically it looks the same on the board, these functions are different. Let's look at these real quickly, just so we can get a handle on it. This is a little bit different from what I've described. I've written down the binomial sampling distribution. And so most of you from probability class will know that I can do inferences on the sum of the xi's, or I could give you all the xi's. And we can kind of see that in this form of everything. So when I write down the sampling distribution, it looks like this. And the only place the xi's come in are through this function, sum of the xi's. So we notice that this function only depends on xi's through their sum. And you would have to, work through a little bit of math to show this. But it doesn't matter what the xi's are. All I care is what the sum of the xi's are. And so a binomial sampling distribution looks like this. So binomials is going to be f. It's the distribution of the sum of the xi's. So I could give that a name, but I'm just going to leave it in as sum of the xi's. And this looks like this. N choose sum of the xi's. I goes from 1 to n. P sum of the xi's. 1 minus p n minus sum of the xi's. And so this formula describes the distribution of the sum of the xi's. That's our new random variable. And we can give that a name if we wanted to. I'll just leave it in as sum of the xi's. And everybody in this class has seen this multiple times. This formula and that formula have the same shapes. So in terms of the sum of the xi's, the only thing that's different is the normalizing constant. And so binomial distribution is just talking about the sum. It doesn't matter how you got there. So if n is 10 and the sum of the xi's is 6, I don't care which order the ones and zeros came in. And that's what this does, is it just counts the number of rearrangements of the ones and zeros that we don't really care about. So inferentially, you could give me all the ones or the zeros, and I would be thinking about my inferences the same as if you gave me the sum of the xi's. What you have to tell me up front is that everything is IID. i.e. it's exchangeable, so I don't really care. So how you give this to me? Just as a prelude, this is a sufficient statistic. So the inferences on P only depend on the xi's through some of the xi's. We'll formalize that later. So in chapter 6, after we get through this lecture, we'll jump right into that stuff. Most of you know this already. If you don't, you're not in bad shape. When I went to grad school for the first time and sufficient statistics came up, I was one of 10 people in my cohort, and I was definitely the only one that didn't know what a sufficient statistic was. I felt like I was way behind. It took like 10 seconds to clear that up. So we'll get there if you don't know all of this stuff. So I'm kind of repeating things that I hope you know, but if you don't, there's a 10 seconds in your future that everything will click. And I'll give you a mathematical formulation of sufficiency. What I've drawn right there is the binomial distribution. And so what it says is that for n being equal to 10, so this is just an example, I have to fix n if I'm going to sample from all of this, and I need to fix p. And that's what this thing says. P is fixed, some of the xi's is random. And so these are the various probabilities for the different number that could be your realization of your sum. So the sum could be 0, it could be 1, 2, all the way out to 10. It can't be 9.5. It's discrete. So it's things that we're counting. And so this is the probability mass function for everything. It's a histogram that I can draw of some sort. But this histogram is really special because it integrates to 1. So all these probability values that you would see over on the left-hand side, I didn't write given P, but I meant to. And sometimes you'll see people write it out like this. Maybe they'll put an R there. And if it were me, if I were writing things out for people, my typical notation would be to give P and tell you what it is. And some people will suppress that notation. But all these probabilities add up to 1. That's what the sampling distribution looks like. So it's a distribution that lives in the space between 0 and n, and it's discretized. Here's what the likelihood function looks like. Now I need to tell you what n is again, and I probably need to tell you what the sum of the xi's are here. So this x right here is representing some of the xi's. So that's my random variable. And I've kind of shortcutted that. And I've changed the notation on us real quickly. But this function, the likelihood function, is a function that lives between 0 and 1. So it's a function of the parameter space. And so algebraically, these two equations look about the same. This thing is just off by the normalizing constant. Later on, we'll figure out that really doesn't have a lot of info for us. There's nothing to do with P in this function right here. And so if I draw this as a function of P, and I plug in what the sum of the xi's are here, and what I did is I plugged in sum of the xi's was 3. So I observe the data, it's fixed. So this right here is sum of the xi's is 3. I could write it down like that. So I can replace the whole vector of x's with some of the xi's because they have the exact same information about P. Basically, it's saying that the shape of this function is only determined through some of the xi's. So I've said the same thing over and over again. Exactly the same thing in lots of different ways. But this function lives between 0 and 1. And it's going to peak at the point where sum of the xi's divided by n is going to peak right there. And in our case, that's sum of the xi's is 3. And it's 10, so that's 0.3 where this thing peaks. Stephen?
What does the y-axis represent in this case?
Nothing. So, almost nothing. And so, we wrote it down. I ended up making it so it normalized. So it integrates to 1. I think it's the way that I wrote this down. It looks like it does. But it's totally arbitrary. So, in terms of this height, being whatever it is, 0.27, 0.275, I don't know, we could figure out whatever that thing is. It doesn't mean anything. And that's why I wrote down proportionality. So I can multiply this by any positive constant and it's still the same likelihood. And so, very good question. It turns out I could compare the likelihood of, let's say, 0.1, and that would be this height right here, and I could compare it to maybe 0.4, and that would be this height. And so if I take a ratio between those two heights, that thing means something. And so likelihood functions are self-relative. So the y-axis doesn't mean anything. So to say like a likelihood is 0.99 and thinking that's big, I have no idea what that means until you tell me about all the other values, and then I can compare them to each other. So multiply by any positive constant and it's still the same likelihood function. You multiply by a negative constant and all of a sudden you muck the whole thing up. So it can't be negative. This thing is supposed to be positive. Don't multiply by 0 either. So any non-zero positive number, same likelihood because it's all self-relative. Hopefully you all know that. In books, in papers, sometimes people write this down and they'll say, here's my sampling distribution, and they'll recycle their notation and say it's their likelihood. And it's very irritating when you're a first-year graduate student to see things like that. And it's like, couldn't you have just taken the time to use Dr. Lumen's notation? People use their own notation and they expect you to understand what it means. So I've gotten over this a long time ago, but people have a hard time sometimes writing down their likelihood functions. So all Bayesians know how to take a sampling distribution and turn it into the likelihood function. A lot of times they throw off all the junk. So I could have built my likelihood function out of this, right here. And this thing right here is totally arbitrary, the positive constant. So this function and this function are the same in terms of p. So if I took my sampling distribution and then I plugged in some of the xi's, I just turned it into a likelihood function if I tried to let this vary as a function of p. So this function and that function look to be about the same, but they're off by a positive constant, and in terms of the likelihood function, that positive constant doesn't mean anything. That positive constant that we wrote down normalizes the sampling distribution, which is different. So we don't even need this, but we'll get into that later. So what I want you to think, just before we get into sufficiency, this function in terms of p, and this function in terms of p, while they're different heights maybe, they have the same shapes. So exact same shape. And that's the information that we use when we do inference. Okay, so likelihood functions and sampling distributions look wildly different when you treat them as a function of their two different arguments, but algebraically on the board they look the same. And that's where all the confusion comes from. I'm going to be specific about my notation and usually tell you whether or not I'm treating it as a sampling distribution or a likelihood function by changing the notation. That is not common between all statisticians. Sometimes people write likelihood functions, they'll flip those arguments around. And that's very common. But they're telling you it's a likelihood, so they're telling you it's a function of the parameter space and not the sample. Why do they do that? Sometimes I think because it makes Bayes' theorem look a little bit better. So it makes it look like this equation right here doesn't have this flip. And they like that. I like the bar to mean something. And I like the bar to tell me what's constant in everything. So again, this is just a pill that you have to swallow and get over it. It's all just notation. And I think this picture helps us to think about it. Trouble with the normal example where a lot of people start is the functions live in the same space, they're continuums, and they're just centered at different places. And so this can show you that the likelihood function and the sampling distribution can live in entirely different spaces. Okay. We're going to go into a simulation in just a moment. I want to tell you about beta distributions before we do that. So beta distributions look like this. So I'll write down F to denote that it's some distribution. It's a distribution over a parameter. I'll call that parameter P. And P is going to live between 0 0, and 1. And it's going to depend on some arguments. Now, when I talk about betas, I'm going to say beta a whole bunch of times. I'm going to talk about the beta function, and it's going to have parameters alpha and beta. So I've used beta twice already, and they mean different things, so bear with me. Beta distribution, and it has two arguments, alpha and beta. So be careful with this. I'm going to use beta a third way in just a second. But they look like this. They're proportional to p to the alpha minus 1, 1 minus p to the beta minus 1. If I wanted to make this equal, I need the normalizing constant. So I would have to write down p to the alpha minus 1, 1 minus p to the beta minus 1. How do you figure out what your normalizing constants are? You integrate over the whole space and you divide by it. So it's the same probability calculation that you're used to doing. And I integrate over p. This goes between 0 and 1. This is called a beta function. So I just use beta in a third way. So it'll keep you on your toes at 9 a.m. in the morning. Which beta is he even talking about? So I'm just going to write it down the way that's pretty common. So this is called a beta function. And it's a function of two arguments. So it's a function, not of p, because I've integrated away p, but it's a function of alpha and beta, the parameters. So it's a function of these two arguments. So beta function, and sometimes people write this down as beta, right there, to denote it. So let's go through that again. This is a beta distribution. It lives between 0 and 1. It maybe looks like that shape that I wrote up there, depending on what the arguments are. It's a function of two parameters, alpha and beta. And so me being me, I always tell you what the arguments are in the function. And I write them to the right-hand side. Not everybody will do that for you. So, but I do it. I even do it in my papers. So I'll write it down. If there's a whole bunch of arguments over here, I usually give it some like bold-face notation so I don't have to write out some long set. So I'll suppress it. But I usually like to write this thing down so that you know what's given. And I do think of it as a conditional probability. If you don't want to, that's okay. So you can think about it however you want. So beta distribution, this thing right here, F, P, alpha, and beta, looks like something. Maybe it looks like that. And it's a function of these two arguments, and this lives between 0 and 1. So this is going to come down. And it values greater than 1, it's 0. And it values less than 0, it's 0. So it only has positive mass in that interval. Again, this normalizing constant that we're writing down makes it so that it integrates to 1. And beta distributions are useful for modeling things like probabilities, because probabilities live between 0 and 1. So it's not the only distribution that you can think of to model probabilities, but it's a useful one, and it's quite flexible, and we'll see that in a moment. So beta distribution depends on an argument beta and alpha, and the normalizing constant is a beta function. And this part right here, I'll call the kernel of the distribution. It has all the shape in it. So this is the beta kernel. So fourth usage of the word beta. That's your beta kernel. It's the shape of the function that you're looking at. The normalizing constant, the beta function, is used to normalize it so that everything under that curve adds up to 1. Who's seen beta functions, beta distributions and beta functions before? Anybody not see it? Is this totally brand new? Maybe you've heard somebody talk about it. You get to play with it from now on. I think at least maybe people have seen it. I remember being overwhelmed, you know, when I took my first grad probability class. There's so many distributions. Yes, there are. So there's even more than you know about. And by the time you become an expert, a PhD, a Nobel Prize winner, there's still more distributions than you've ever seen before. So there's infinity upon infinity upon infinity of distributions. And the name of the game as a Bayesian modeler is to create the right one that models everything for you. How do you do that? Trial and error. So if you saw Andy Gelman's talk earlier this semester, he tells you something about an iterative process to refining everything. So this isn't a modeling class. I'm going to tell you about the mathematical properties of everything. Later on, you'll learn about how to use this stuff in modeling context, and I'll sprinkle some anecdotes around. We'll see this in a very simple example in just a moment. So any questions before I move on? Okay. So bisampling distribution looks like this, which induces that likelihood function. Here's the part I want you to notice. This looks an awful lot like a beta kernel. So the likelihood function looks like a beta distribution. It's not a distribution yet until I apply Bayes' theorem. So the idea is to apply this formula. I take the likelihood function and I multiply by a prior, and I get my posterior beliefs, and this will model at least what I think the probability is. So this is a fun problem because I have the probability over a probability parameter. So this is probabilities on probabilities. And I've had people say, how can you even think about such a thing? And I usually say anything I'm uncertain about, I'll put a distribution. So anything that you want to quantify, you can build uncertainty around, and as a statistician, I like to build probabilities. So that parameter is just a probability, and I'm going to put probabilities on what I believe that probability is. So I've had people say it's too much to think about. You'll get used to it. I don't know, I think it's very little to think about, but I get it, that you're recycling the word over and over again. But anything you're going to estimate, you probably want to put a probability on it. A Bayesian will do that explicitly, and non-Bayesians will at least quantify uncertainties maybe in other contexts. So anything you're interested in estimating, build uncertainty around it and say what you're uncertain about. Don't tell people, here's my best guess. Tell them what your best guess is and other good guesses. Peter.
So with that in mind, how many levels deep would you usually go? Like, so with alpha and beta, I mean, you could put a distribution on that, and then with those parameters, put distributions on those.
Yeah, you have to stop at some point.
Yeah.
So if I ended up putting a distribution in an alpha and beta, then that distribution would have parameters as well. I'll talk about the name of those parameters. We'll say the word hyperparameter in a second. If I did that, it would just change the distribution, and it would be a function of those parameters. So I guess I would go as far as I needed to have the right flexibility in the model, and then I would stop. It's a good question, but you have to stop somewhere. Okay. This, in our problem, looks a lot like a beta kernel. And there's something called a conjugate prior. And so a conjugate prior is such that the prior and the posterior live in the same family of distributions. So I don't mean something as broad as the exponential family. I want you to actually define what the distributional family is. So exponential families are too broad, that's families over families. So I want to talk about just families. So let me give you a definition. And we'll be using this throughout the class. I think this is about as far as I'll go in the Bayes, but of course we have review sessions and we can fill in all details if you're curious about it and you want to get ahead before you take formalized Bayes classes. But a conjugate prior. So it's got a pretty easy definition. So if pi p is an element of some family of distributions. So, i.e. maybe a beta, or maybe a normal, or maybe an exponential, or maybe a Poisson, or maybe a gamma, maybe an f, maybe a t. But not the whole exponential family thing. Not the thing that subsumes a whole bunch of those. So, i.e. beta, or a normal, or a gamma. And we'll touch those later. You've at least seen it in terms of your homework, maybe what gammas look like. I mean the or in the exclusive sense. So not all of them simultaneously, not some super family. So if my prior lives in some family and my posterior lives in the same family of distributions. So same family. Then we say the prior is conjugate. So I'm just giving you a definition. So if I can pick a prior such that the distributional family doesn't change once I multiply by the likelihood, you don't even have to think about this stuff, it's just normalizer. But if I can slide the prior through the likelihood, and that's the same distributional family, I say that the prior is conjugate. And the reason we like to do that, at least the simplest reason I can give you, is because it makes everything easy. But there's other good reasons. So sometimes these priors will have other properties that we'll like. And throughout this class I'll say there's other properties. And sometimes I'll even tell you what those properties are, and you'll be like, well, I want to know more about that. This isn't that class. So we're going to mostly tread on conjugate priors, but there's other good reasons that you might use conjugate priors. So reference priors tend to be conjugate, Jeffrey priors tend to be limits of conjugate priors. And so using conjugate priors is sometimes mathematically justified, and it gives you an optimal property in the posterior. Right now, I'm going to describe everything as the conjugate prior makes everything simple. So if I know how to compute probabilities in the prior space, and it's conjugate, then I know how to compute probabilities in the posterior space, because it's the same distributional family. So let me just ask a question. What is the conjugate prior for this analysis? Over here.
A beta.
It's beta. So there's the big 7. And you guys do this, I think. It's hard to know. Some of you may not have studied Bayes ever before. So if you haven't, congratulations. This is an awesome lecture for you. At least for me. So the conjugate prior. In this analysis, if I look at my likelihood function, p to the sum of the xi's, 1 minus p, sum of the xi's, n minus, right there, is beta. And it's any old beta. It has 2 parameters. So I haven't defined specifically what the distribution is. I've only talked about its family. So what I mean in terms of family is this is a whole collection of beta. If I change alpha and beta, these numbers right here then I change the actual distribution. So if I think about this as just a function of those two things, there's an infinite collection of these distributions. It's not an actual distribution until I tell you what those parameters are. In a Bayesian context, meaning that I'm using that distribution as a Bayesian prior, I usually call these parameters hyperparameters. So there's a lot of disagreement on vocabulary and notation, but I've never heard anybody call this something different. So the parameters that underline your prior are called hyperparameters. I'll write that down. Params in your prior. So they might define what you presuppose the parameter P is in the first place. They might also model your ignorance. They might also be defined for mathematical properties of your posterior. I want posterior to do something. On average, I want it to do something. Maybe I want the intervals constructed from it to have some property. And I might pick those parameters based off of that. So in our case, our Bayesian prior is just going to be pi t. And I don't really care about the normalizing constant in all of this. I can integrate and normalize my posterior later. So what I'm going to do is I'm going to write down the likelihood proportional to something where the constant out in front is the simplest thing that I can write down. Usually I make it 1. And later on I normalize. So this is going to be proportional to p to the alpha minus 1, 1 minus p to the beta minus 1. And so you might say, how do I know what the conjugate prior is? You stare at the likelihood, and you think about the function that you multiply through the likelihood that it preserves its functional form. You might say, is there a trick? And there is. The trick is to know all your distributions so that you recognize it. And there's no simpler way to do that. If you don't know what the distributions are, it would be a really hard thing to do. So I will tell you this over and over again. Every time you touch a distribution, write it down on a piece of paper, stick it to your refrigerator, and stare at that often. Probably know things like the mean and the variance. Does anybody know what the mean of a beta distribution is?
Isn't it alpha over alpha plus beta?
Yeah, I like that. So it's alpha over alpha plus beta. And we would need to check this thing out and make sure that lives between 0 and 1. What I didn't tell you about these parameters is that this has to be greater than 0, and this has to be greater than 0. So I should have been polite and tell you where those things live. They can't be negative. If they were negative, it would flip this thing around in all kinds of funky directions, and it would make it non-normalizable. And so if these aren't positive, you won't be able to come up with that constant down here. It won't integrate to 1 on you. Does anybody know what the variance is? This one's harder.
I think it's alpha over alpha plus beta times alpha plus beta 1, or plus 1.
There's a square in there, isn't there? So you're close, really close. So play around with it. I don't ever ask a question where you need to know that, but it's still a good thing to look up right on the refrigerator. Again, on a piece of paper so that you get it right back. Okay, so we're moving pretty fast through this. I think we got to play around with this a little bit, kind of understand it. But my Bayesian posterior, once I put all this together, looks like this. So I'm going to get rid of definition of a conjugate prior. The prior that we're using is beta. If we want to use the conjugate form, why? For at least for right now, because it's simple. But there are more compelling reasons, very compelling reasons. Everybody will use a beta in this problem, unless you tell me something about P. So with blind knowledge of P, i.e. you don't know anything, you'd probably pick a beta. So my posterior So again, I didn't pick my prior form because I thought something about P. I picked it because it was mathematically convenient. Also, there's other good properties. So this is going to look like the likelihood. And this is going to be the prior over here. And it's going to have two arguments in there. So this is going to look like P to the sum of the xi's. I goes from 1 to n. 1 minus P to the n minus sum of the xi's. And then I'm going to multiply by my prior. This is going to be P to the alpha minus 1. 1 minus P to the beta minus 1. So I can rewrite that down. Again, I wrote down proportionality because I only wrote the likelihood up to proportionality. So I could carry the normalizing constant on the prior, but it's still only proportional because the likelihood function was proportional. So I'm just going to toss that thing because it doesn't help me. So this looks like P to the sum of the xi's plus alpha minus 1. 1 minus P to the n minus sum of the xi's. I goes from 1 to n plus beta minus 1. And so this looks like a beta. I could normalize it if you wanted to and integrate everything out. And I guess on the computer I'll do that so that everything normalizes to 1 and we have scale that's easy to see in my visualizations. But I can already recognize that this is a beta distribution. And it has two arguments. And where do I look for the arguments? I look for the arguments in the thing that's over to the minus 1s. So this was a beta, and I recognize its parameters by locating the minus 1, and I grab everything to the left. If there wasn't a minus 1 there, I'd add a 1 in, and I would subtract off a 1. So it turns out in the prior, it always has the minus 1, and I always keep that dangling. So I never try to soak it up, because I know I'm going to use it to recognize the parameters of my distribution. So this is going to be a beta with this argument right here. Sum of the xi's plus alpha, and it's going to have n minus sum of the xi's plus beta. Those are my arguments. So this is a distribution that I can maybe calculate probabilities off of. And I'll show you what that distribution looks like in just a second. So because I know what the functional form of the prior is and its conjugate, then I know the functional form of the posterior. And it's kind of nice. It's like sequential updating. So once I see data, I'm just updating the arguments of the distribution that I'm working with. That's what conjugate priors do, is you're just updating with the data. The data comes in through some of the xi's. I guess you can think of n, but usually that's fixed to you. But it's just updating the arguments. So you're taking the hyperparameters and you're updating them in their posterior form with data. Let me show you what this looks like. But a Bayesian is going to do inference based off of this distribution. They'll normalize it and they can compute probabilities for you. The full Bayesian answer is the full distribution. So let me just ask you a question before we continue. What would you pick alpha and beta to be in your prior? If we use this prior, what would you want them to be? I have to pick them before I move forward. Otherwise, it's not a real analysis. I can't compute a probability, but once you tell me alpha and beta, the hyperparameters, I can compute a probability. So what would you pick these to be? The hyperparameters.
Successes, failures.
What's that?
Successes and failures.
They have something to do with successes and failures, but I'm asking you for actual numbers. So, but that is what they're representing in some sense, is they're kind of your a priori, what you think the number of successes to failures are. If it's just that, I could say maybe the successes are 10 to 1, but I could also talk about 100 to 10, and those would be different things, because it would change the variance. Anker?
Well, if you're completely ignorant, you could do 1 and 1.
1 and 1. So Anker says 1 and 1. So he kind of likes that. It makes it uniform across the space. It's not the best answer. It's not the one that I would pick, but you wouldn't do that bad with it. And so let's go with that. So, and then I'll tell you about some other possible choices. If you're waiting for it, you could ask Jess. Jess, what would you pick?
1/2.
1/2 and 1/2. Half and half is what Jess would pick. We'll explain that later. But pretty close to what Anker said. He's kind of just saying, let it be flat across 0 to 1. And I kind of like that answer. So I wrote a piece of code that's going to simulate data. I'm going to have to bring in what P is. I have to have the truth in there. The only place I'm using the truth is in simulating the data and plotting against the truth, so you know what the truth is. Then I'm going to take in these two arguments, alpha and beta. Those are my hyperparameters. In iterations, it's n. So I need to feed that in. So let's have a look. I've anticipated Anker's answer, and I plugged in 1 and 1. Because I knew that's what everybody's going to want. Jess has all kinds of reasons for picking something different. And she'll tell you that if n were big, it won't matter so much. So let's just look at it. So boom, I made a plot. It's got the prior, that's the dashed line. So if you look at this, when this is 1 and 1, this is a 1, that's a 1 now. 1 times 1 is 1. That's a uniform distribution. So that's kind of cool. So that's a uniform distribution. But I ended up plotting, that's my prior, and I plotted the truth. I'm going to flip the coin once. So my first coin flip is a 0. I got a negative. And what I drew for you was the likelihood function, and then I also drew on top of it the posterior distribution. Now the likelihood function times 1 is the posterior, so the likelihood in the posterior will be exactly the same. And it's that negatively sloped line. What does that look like? It looks like 1 minus p in my posterior. So my first likelihood function is just 1 minus p. We'll go through this a little bit slower next time, but let's just flip the coin again. Oh, I just saw a success. In the posterior, just bent. Looks just like my likelihood because Anker told us to multiply by 1, and I guess that's okay. So what it's telling you is that the probability, or at least the density on this function of being 0 is 0, because I saw 1. And the likelihood of p being 1 is also 0, because I've seen it 0. So it can't be 1 and it can't be 0, it's something else. We know it's 0.7. If I keep running this curve is going to bend all over the place. You can think about the delta method. It would always build a symmetric curve, the normal distribution for this example. But the posterior distribution looks a little bit different, and I've normalized it all for you. And here's the truth. And my posterior distribution is saying the truth, I think, is in this massy part. Maybe that's a little off to the right-hand side. It's not exactly in the middle. What do I think the truth is? Maybe right around there. But I don't think that's a bad answer right there because it's right over here. As we see more and more data, this distribution will start to peak around the truth. I'm going to come back next time, walk through this example real slowly, generalize a little bit for you, and then we're going to move on. Homework problems will hit the website later on today, so extra homework problems. You will turn in whatever homework on Wednesday, not with these problems. That will be a different assignment number. I'll give you a due date. It'll be due in about 2 weeks. Okay. Also, Monday will be a review session at 5:30 if you'd like to attend. Thanks, you guys. Enjoy the weekend. It should be warm, maybe a little bit drizzly, but still good stuff.